Hello, welcome back. Today we're going to be talking about the rocket equation. And so, suppose you have some rocket, has a mass, and it's ejecting fuel. And it's got an external force. And it is moving with some velocity. Let's think about, what is going on here. So why does this work? First of all, this works because of the conservation of momentum, or at least Newton's third law, which says that the force acting on an object 1 and 2 is equal to the negative force acting between 2 and 1. Momentum is going to be conserved as we have so if I'm on a boot, if I'm on maybe like an ice raft, and I have this guy sitting there, he's gonna have some momentum. If I throw an object, this object is gonna have some momentum now. And in order for the total change in our momentum to be conserved, I'm going to have to pick up some extra momentum, right, in the opposite direction to cancel out the momentum of the object I just threw. So that's exactly what's going on here. The way we want to analyze this is we want to think about the change in our momentum. So here's momentum. Let's see what the m velocity is a function of time. So let's think about what's happening with a rocket here. At a time, so the momentum at pt plus dt, what is happening? Well, our mass is changing. And here dm is less than 0. And our velocity is changing as well. So it's some change in our mass, some change in our velocity. And the fuel is being ejected. And it's going to be ejected with a momentum, which is going to be negative our change in our mass times our velocity minus this external velocity. And what can we do here? So we add these two together. And our change in momentum, dp, which we know is 0, is going to be pt plus dt plus p. We can move this through with FOIL, right? So FOIL this through. We're going to get, actually my bad, this is not a plus, this is a minus p. This is going to get us mv plus mdv plus dmv plus dmdv minus dmv minus or plus dmv external. So let's look at anything that can cancel out. What can we do with this? Okay, so we have a dm mv here. This because these are infinitesimally small as they approach 0. So the limit is approaches 0. This approaches 0. You can cancel this guy out, and we're left with mv plus mdv. And then minus p, so minus mv. And so these terms cancel out. So what do you get? We get m times dv equals or plus dm, and our external velocity is equal to 0. So we can move this diff around. mdv equals negative dm v external. And obviously, if we were to, divide dt over dt, we get this final form, v dot equals negative m dot v external. So this is an interesting set of equations. This is an interesting set of equations here. And how can we solve for v? So we want to get v. How can we do that? So the first thing we're going to do is, well, we're going to divide by m, separate these. You get negative m dot over m, and then v external is a constant. We get v minus v naught, and then we're going to get this integral from t to 0 of negative m dot s over ms ds times v external, and this is going to give us negative v external times the natural log of m minus the natural log of m at 0. So I'm gonna write that there. And so what does that do? We can use log laws, lm over m naught. And we move that negative sign. V external is the natural log of m naught over m. So notice I moved this negative sign inside, and that's going to swap their position. So we get this final equation for velocity. V is equal to our initial velocity plus our external velocity times the natural log of our initial mass over mass. And this is our rocket equation. So yeah, not too shabby, not too bad. Next up, we're going to go into moving. So this is going to represent our equation of motion here. So, and then obviously, okay, so I'll just write down both equations just to be concise. All right, so that's that. In the next one, we're going to look at some other stuff with rockets, maybe answer some questions. All right, thank you.